Okay. In the last class, we introduced a fundamental definition of information in this form related to an event x equal to xk and whose probability was p of k. We said that by definition the information associated with the occurrence of the event x equal to xk, where x is defined over the ensemble capital X, was log of 1 upon pk, and we decided to choose a base of 2, so that the unit of our information is bit. By looking at this expression, one can perhaps satisfy himself in terms of this following A, B, C, D. This definition is acceptable because it goes with our common sense. For example, if P of k is 1, that means the event is certain to happen, then do we say by common sense that, well, I get some information, I get something new, it was not unknown? Not like that. So, I of xk is 0 in that case. As per this expression, it is like that only. So, this goes well as per our common sense. The second one, that if the probability is less than 0, then I say that yes, it was not known to me, so I have got some information. I get positive information, we say. Okay. So, when the probability is less than 1, yes, anything between 0 and 1, we say that we have gained in information really. So, information should be positive in that case, and we see that yes, it is, information is positive by this definition. Then if I have experience of two events, okay, in one case the probability was pi and in the other case the probability was pj, it is obvious that for the less probable or more improbable event, I get more information. That is what is indicated in the third one, is not it? I get more information if the corresponding probability was less. Okay. The last one, which is specifically true for statistically independent experiments, joint experiment, but the two experiment parts x and y, they are independent statistically. Okay. In that case, if I learn something from one experiment, if I learn something from the second experiment, and if two experiments were independent of each other, then is it not that I learn something from the first one plus something from the second one? That means information by nature at least is additive when the two experiments are statistically independent, and that is what is indicated by the last point, that the information, okay, over a joint experiment is really additive when especially the experiments are statistically independent. Okay. So, this definition hence is acceptable. Okay. But let me tell you that this definition is not the most complete definition of information in the most general form. You can define information in your way as well really, but for the study of digital communications, this is a well accepted definition. Okay. In fact, we also said in the last class that one way of starting the basics of information theory is defining this kind of information fundamentally defined over a single experiment or single ensemble X. Fine. Another way, as per some authors, experts, is to talk first about mutual information and then show that this kind of information is a special case. This information also then named in a somewhat different manner, and this information is called as self information in respect to another kind of information which we named as mutual information. So, self information or this kind of information is a special case of mutual information, okay, as per another group of experts really. So, we did introduce the basic definition of mutual information. Yeah, please. More.
But like suppose the English alphabet is there, and then suppose E is probable to occur more than suppose B.
Right.
So, but E is as important for me as B is there. So, like, what is the information gain? What extra thing am I getting if I get a B instead of E?
Well, that is a good question. What he says is, he is as if receiving a text wherein suppose in a particular place E was expected, whose probability of occurrence is much higher than say x in that position really. Okay. his question is how do I get say more information if I get x here rather than b? Is that the question? Yes. Any answer? Yes, please.
So there are less number of words with the letter X. So you can the receiver can guess the more words. Less I mean they get more accurately.
Well, so instead of b, if I get x, which was less probable, then as per this definition, we should have got more information. But the fundamental problem is that, but after all, it's a mistake really, and the purpose would be served if we would have got b in that place, I mean e at that position really. Or how come by receiving x I get more information, more fundamentally? Yes. So one suggestion was there that by reading the full word, the interpreter or the user may make out whether x there is a mistake or whether e was more likely. Okay, or yes.
Yeah, correct. More number of words, sir.
Yes.
You don't, when E comes, you don't know which word you're talking to. So next comes your list of words that maybe the one that is coming is
Right.
narrowed down.
Right.
That way they're getting more from when X comes further when E comes.
Okay, I'll try to. Yes, there is one more suggestion.
E is more probable than P, suppose.
Yes,
So if E comes, there is lesser information because there is
that's what I tried to say. But he has posed a problem, which is also meaningful.
less randomness because if E comes, it is less random.
Right.
If B comes, it is more random, and if more random means we are getting more information.
You are accepting my definition. He is contesting my definition. Is it not? What he says is the how come? How?
The digital code of the less probable word may be more and the digital word for a more probable may be of
That's you are now the designer. You are telling the details of how you have designed the system. But he is not interested in that, in how the system has been designed. His problem is very fundamental. He is a user. To an user, that is a real problem. But let me tell you, it is all because you are trying to interpret. You are trying to see the association of a particular letter with other letters. You identified that the received letter of B of or X, whatever it is a mistake. Okay, and something else was expected. And if the word is such that you could identify clearly that the E was the correct letter in that position, rather than that you have got something. So the fundamental issue is again here is that you are talking about not letters in isolation, but about their association in the form of words and sentences.
But this is actually you have a database basically that how many types of words what you are expecting. It's because of your database, and this is not supposed to be in which way. Like this will help if we try to like remove a error correction or something like that. But this is because you have a previously stored data with you. So if you don't have a previously stored data, then what difference the same information would be with the X or with the B?
Let us say that ultimately the user may be interested in that kind of usage even, that okay, what is the purpose of transmitting these letters? Ultimately it's a text, meaningful text which has to be recovered. Okay, so for recovering the text, if he is thinking of an automated one, he may have a database by which he can compare whether any word has been missed or whether any letter in a word has been missed and things like that. The interpretation of the whole text, that is also a very meaningful process really. But our definition so far is limited in the sense that we talked about an event of one letter. In your example, occurrence of E or I mean lack of that, or occurrence of B or X is the event. We can expand this idea, like for this particular application that he talks about, we could also define an event consisting of several occurrences of letters such that we can define an information in a full word even. Okay. Your application of association of a letter with others is fundamentally driven towards finding an word and its meaning and things like that. When it comes to that really, the event also should have been defined appropriately. Okay. When you are trying to understand whether a word it's a meaningful word, whether the sentence is correct, you have to define your events not necessarily in terms of letters. When you do that really, again it falls back to my domain of definition really. Suppose you have defined your events as receipt of one word. Okay. Now if you receive a word which is more unlikely compared to a word which was very common one, A and the kind of thing, then I say as per this definition only that you received more information when you received a very unlikely or unusual word compared to A and B. Does that make sense? That is what is implied in this definition really. So, there is no violation actually, it is again the question of how you are interpreting, how you are utilizing, how you are defining your event and you are utilizing this definition. Okay.
It's basically like a source coding, like you are trying to reduce the bit rate.
No.
Like in a Nokia cell phone,
Right.
you have like one letter like key 1 will ABC.
Right.
So if you are trying to type word, then you type, it's a 4-letter word and it's in the database of the dictionary. So you just press it the 4 button. It will interpret it itself whether it was A, B or C. And it will require lesser number of bits
Right.
than actually required. This is a kind of source, like you are trying to predict because of your previous data and you are trying to reduce the number
Okay, that's again one very good use of a short dictionary, okay, for conveying a limited number of words, okay, and that too using minimum number of bits, okay. But so far, I mean, what his problem was and what my point here is, I mean, they are not necessarily targeted to that application. Those applications are fine down the line, okay. See that this kind of short messaging service is possible is fundamentally because those short letters or words, short dictionary can become conveyed easily, okay, at a data rate which is good enough for accommodation within the given bandwidth in the GSM system. It is something like that. It is more involved and more related to the system and its other specifications. Okay, but our problem was more fundamental really. The problem was fundamentally how we are defining my event really. If something more unexpected comes, we in general say it conveys more information. That is what is the implication of it. Okay. Shall we go ahead? So, then we will try to take a somewhat roundabout way bringing in this parameter of mutual information, okay, and getting some more insight, because this concept is definitely a powerful one. It will also help in understanding some features of what we have modeled earlier as, or what we have named earlier as a discrete channel. Sorry. This definition I had given, I made a mistake in the notation. I mean, I am modifying this. Please note that we will by convention introduce a semicolon here between xk and yj, the two outcomes of the two experiments x and y. Okay. So, this is a symbol for the mutual information defined over a joint, in this case a two experiment ensemble x y separated by semicolon, okay, and by definition this mutual information is log of 2 this. From now on I will use the base 2 and mention for quite some time at least that the unit for this information again is bit. Okay. So, this is the ratio of the conditional probability and the probability of occurrence of x equal to xk. Fine. So, mutual information fundamentally is the ratio of, is the logarithm of the ratio of two probabilities. Okay. Numerator is the conditional probability of x equal to xk given that y equal to yj has already occurred from the experiment y, okay, divided by, in the denominator it is the probability of x equal to xk. Okay. One form of interpretation of this definition and expression for mutual information is that it is, should read a bit slowly here, it is the amount of information provided about the event x equal to xk by the occurrence of the event y equal to yj. That means it was a joint experiment. Okay. In this expression we are assuming that y equal to yj has occurred, and then from this occurrence how much information you get about the other occurrence, that x equal to xk. Okay. So, this amount of information is called as the mutual information. Do not ask me right now why it is mutual, we will see that gradually. Why it is called mutual information? One sense is that it is defined over a joint ensemble of x and y. Now, this mutual information is a very relevant parameter in several contexts. I will take one example. Yes, please. Mutual information. Yes. X and Y. Yes.
Simply P of
XK. Yes.
P of xk.
Yes. 1. So the mutual information is 0. Yes.
In the previous slide, you had given one formula IXY.
Right.
So
That IXY was not the mutual information. Okay, good point. You are referring to this slide. Okay. See here in D, it is not mutual information. It is the it is a joint event xi yj. There is no semicolon in between. Please note that this is a joint event. So that there is a statistical experiment. Okay, I have defined an event. My event is now so defined that x equal to xi and y equal to yj. That is my event. And now I am trying to find the information, this kind of information, which is defined over the joint ensemble. So I am writing x capital X semicolon capital Y. Okay, that in x equal to xi has occurred, in y equal to yj has occurred. So my event was not x equal to xi nor y equal to yj nor or etc etc. It is and x equal to xi from experiment x, y equal to yj from experiment y, and my event is that it has occurred in like this in both the experiments. So this joint event probability and its corresponding associated information was talked about. Compared to this, here we are talking about a mutual information where I am saying that okay, y equal to yj has occurred. Okay, and then here by this measure I am assessing the amount of information that I know about x equal to xk. My event of interest here finally is x equal to xk. Okay, and I am asking about that only when I know y equal to yj has occurred from the second experiment y. There is a difference. Is that okay? Fine. So I go to the next one. As an example, see, I may consider a situation like this to talk about mutual information someday. Okay, is that I consider my noisy channel. You remember which noisy channel I am talking about with reference to the block diagram of the communication receiver system? It is a discrete channel because the input and outputs are information or discrete symbols. Okay, this kind of channel, I mean, for our discussion in the course, we will assume also to be what is known as discrete memoryless channel. I am writing this for discrete memoryless channel. Why memoryless? This channel for our purposes we will mostly model as discrete memoryless channel, though in general a noisy channel also may have memory. Okay. For ease of understanding, we will consider a discrete memoryless channel. The channel is discrete, it accepts discrete symbols at its input, delivers a discrete symbol at the output, okay, and it's a memoryless channel. By that we mean any particular output, say y equal to yj, okay, will be dependent only on the corresponding or respective input at say x equal to xi at the input. A channel output y equal to yj will be only dependent on the respective input x equal to xi. It will not be dependent on any previous input. That means the channel as if does not remember what else have already gone through this channel. It does not remember anything. There is no trace of this. So whatever is the current output, okay, will guide the corresponding output. Current input will guide the corresponding output. The channel does not remember what all has passed. Can you give an example of such a discrete memoryless channel? I mean a closed one. I mean at least in terms of the physical channel. Yes. Let's go for an electronic communication example really. Yes, man-to-man communication may go beyond our definition of information and may lead to problems.
From one computer to other computer.
Yes. communication between two computers, telephone network is not a good example of a memoryless channel really. Telephone network is highly limited in bandwidth in channel, and usually there are effects of what is known as inter-symbol interference. Okay, if you transmit one symbol through the channel, through the telephone cable or this kind of cable, the symbol energy spills over to the next symbol duration and causes interference. So that is not an example of a memoryless channel usually. Okay, but the same cable over a very short distance is fine, because that kind of spillover is very much related to the length of the cable. Okay, short distance computer to computer communication, yes, is a good example. The cable is a nice quality cable is chosen, and the data rate is so decided that the data symbols or pulses will not overlap with one another, and in that case, yes, the channel does not remember. That is an example of a channel really. There was the third example. If not, say between say in a point to point communication system through wireless, okay, usually there is no reason why the channel should remember what has gone through it. Okay, unless there is some design problem in the transmitter and receiver front end really. So usually many of the propagation channels should behave as a noiseless as a noisy memoryless channel, as a memoryless channel really, but the channel may have some partial memory either because of lax design or because of the fundamental nature of the propagating medium that has been chosen. Okay. So discrete memoryless channel is a good one, easy to understand, and is applicable also in usual cases.
Sir, this discrete memoryless channel can have a delay.
Propagation delay, yes, it may have. For example, the satellite link, a signal transmitted from one place and received at the other point through a satellite link, okay, may be considered as a discrete memoryless channel, okay, with modification, and the link involves delay. So whatever is launched at this point, now if I just try to map the corresponding physical situation, whatever is launched, say xi, if it is launched here at this moment, need not reach the output at the same instant. We need not get y equal to yj at the same instant. There may be some delay involved, but delay does not mean mixed up in the delay really. The previous symbol is delayed by a smaller amount, is delayed by a larger amount, and the current symbol is delayed by a smaller amount, so that they mix up together and results in some kind of memory at the output. Not that way. Whatever is the delay, if it is the same for all symbols, then delay is accepted. So yes, this kind of discrete memoryless channel may have its inherent delay in the corresponding physical propagation, physical medium. Yes.
So do we suppose that information always is positive?
The earlier information that I defined, okay, which we will call as self information, is always positive or non-negative. It may be 0 when the probability is 1, but it cannot be negative.
So but this equation, sir, I mean
This equation you mean the mutual information? Yes, I am coming to that. Yes, this may be negative. Okay, so it is not blindly that any information is negative, is positive. Not that way. The earlier information, which we also call as self information, is non-negative. Okay, but this mutual information, a good point we have observed, is it may be negative in some cases. Yes, it may be negative.
So what is the physical significance of negative?
So what does it imply it being negative?
So you don't gain anything. I'll say when I said the information should be positive when the probability is less, I meant that I gain something in information. So when information is negative, I do not gain anything. Don't ask me if you think of losing anything. So no question of losing really. Whatever you have received, you have received. Okay, but we say it's an indication that well, if information, if you have the two cases wherein in one case you are getting positive information, in the other case you are getting negative information, you will rely or you will try to have the positive information. That's the idea. Ultimate aim of this transmission system is to convey positive information from the transmitter side to the receiver side.
So negative would mean that the occurrence of yj gives us less idea about the occurrence of xk than the actual occurrence of xk.
Yeah, maybe there will be occasions. I have an example to show you that. Okay, so let's wait for some time. Okay, so is this model now accepted? So this is a discrete memoryless channel, the way I am proposing here today, and that's the usual good model for understanding. So I have defined an alphabet here. Okay, X stands for the ensemble at the input, Y is the ensemble at the output. This is the source and the output alphabet. This is the input alphabet. Okay, so in terms of this, I can define kind of mutual information. Yes or no? Yes, it is possible to define mutual information, because as if I have not drawn that, that is implicit. There is another experiment here happening, statistical experiment called X is occurring here. That's the source. Okay, source with the source coding, etc., and all operations of transmitter before the signal is launched to this noisy channel, discrete channel. So this is the first experiment, and channel is as if the second experiment. Okay, so that we can talk about an outcome y, and by common sense we can relate that outcome y is somehow related to this input of x. Okay, so I can define mutual information by the same definition, unit being bits, and now in this context I can define this conditional probability as the probability that as if I have observed y equal to yj, and then I am trying to find what was the probability that x equal to xk was launched at the input. Sorry, I mean there is some confusion here. To make it compatible, allow me to put xi as xk. Okay, in the definition I have used that really. Let me write this as, modify this as xk. That means now looking at the numerator, I can say that as if this probability is the probability of occurrence of x equal to xk at the input to the channel when I have received y equal to yj. Okay, that means after receiving something at the receiver, I am guessing back what is the probability that xk was transmitted. Okay, when I look for this kind of probability, we call this probability as a posteriori probability. The incident has happened, is it not? The symbol I have received, and then I am looking back and asking back what was the probability that x was xk. Okay, this probability is also known as the a posteriori probability. Okay, what was the basic probability of occurrence of x equal to xk is given by the denominator. P of xk defined over this ensemble capital X is nothing but the probability of occurrence of x equal to xk, that is known as the a priori probability of x. Okay, that means x equal to xk had a certain probability which I didn't know at this output end. Fine, that was its a priori probability, and after seeing y equal to yj output, I am now trying to guess how much was the probability really. This probability is the a posteriori probability, is a conditional probability. Okay.
So,
Yes, please.
so you have just defined while defining the channel that x is equal to xk will give y is equal to yj independent of the previous memory.
Previous symbols which have gone through.
So, sir, if we have received yj,
Right.
then it is almost sure that it must have been xk.
No, I can't say that. I can't. That all depends on this probability, conditional probability. That all depends on this conditional probability. I have another example where this issue is addressed. Okay. Well, so in this context, we can see in that with respect to this basic definition of mutual information, it is easy to see. You can read it yourself. That we defined I of x semicolon y. Okay, we preferred x first, we prefer to write x first, y next, somewhat arbitrarily. Okay, similarly one could also write an expression for mutual information in this form of I taking y first, x next. Okay, yj first, xk next, and the definition would be then its log of 2 probability of conditional probability of getting yj or y equal to yj given x equal to xk. I mean looking at in the other way around really. Okay, and it is interesting to see that this mutual information written in a different order gives rise to the same mutual information that we are discussing about so far. Very simple straightforward derivation. And is valid even when the two experiments are not statistically independent. They are dependent, still it is valid. Okay. Sorry. We can separate out the probabilities. I may break this conditional probability in terms of the joint probability. See this expression p xy xk comma yj is a joint probability that xk occurs in experiment x, yj occurs in experiment y, capital Y. Okay, so this is a joint probability divided by this probability of x equal to xk, which is the conditional probability. Okay, and then 1 upon py j, and by rearranging I can get that this I of y semicolon x is nothing but I of x semicolon y. Okay, if you have finished, please think of get back to my earlier noise model and tell me quickly the physical interpretation of mutual information and what is the interpretation of their equality really. Yes, please.
That means the channel does not depend on the direction from which we are giving input and taking output. If we giving input from one side and taking output from the other side, that will be the very similar if we have given input from the output side and taken output from the input side.
Unfortunately not. No, it does not talk about the bidirectional nature of the channel. Okay, this is a concept only. See, for this discrete channel, direction is immaterial. Okay, this is ultimately I will say is a statistical experiment. Fine, but let us not think of direction and then think in our background of the physical channel. The physical channel, if you again get back to my block diagram, you will find that the physical channel includes the modulator and the demodulator. Okay. Now, if I translate his point, then it should also mean that I could inject something at from the receiver, and instead of getting modulated, it modulated fast, then it would be transmitted very feebly through a low noise amplifier to the physical channel, and then in the transmitter end, now it will be power amplified suddenly, and then it would be taken for modulation. The reverse path, if you imagine, you will agree that that's not a direct bidirectional path. So, at the physical level, when it comes to the actual system, it is not correct. Okay. My point is that it is not necessary to bring in the issue of direction, because it's a statistical experiment. The idea, it is conceptual, it is abstract really. When it comes to the physical system, you have to be more careful about the individual systems. In fact, if you allow me briefly, the propagation channel as per our nomenclature is usually bidirectional. Okay. Radio channel is also mostly bidirectional. Modulation channel is not bidirectional. Okay, fine. But coming back to this context really in an abstract manner, it simply means the amount of information that I would get about x equal to xk by observing y equal to yj is the same as I would get the information here if y equal to yj would have if I would have received x equal to xk here, I would get the same amount of information about y equal to yj. Okay. So, even if I bring in the notion of direction etc., that should be limited only for this understanding, should not be translated to the actual system. Good. Yes.
So let's say sir, that yj can come from 3 4 scales like x1, x2, x3 and all that in yj.
Yes.
So and px xk is same for all of these. So
that also is an assumption. Your assumption. Fine. Yeah.
So and the value of p so when yj are occurring, then the probability of x1 is input is quite less. So in that case, the information I should be getting in that case should be more.
See, this you better to make it, I mean, somewhat precise. You see, is there any flaw in this derivation?
No, sir. What my point is, sir, what I think is that the definition we define for mutual information.
Yes.
I think it's more meaningful if we make it the other way around. In the numerator, we reverse the numerator denominator. So because what I am saying is that if x1, the probability of x1 and yj having a less correlation, in that case we should have more information on our hands rather than getting a negative information.
Okay, let me say, I mean, in my example, I will show that if this also models the basic issue of some kind of decision strategy in the receiver. This particular example of noisy channel, etc. Okay, and there we'll see you'd love to say that when the mutual information is positive, you know about what was transmitted more, rather than receiving a negative mutual information and saying that now I know what was transmitted, something like that. This definition, the way I have put it, it's more natural, is my point at the moment. Okay, let's see for some more time. Okay, so this derivation is okay, and now I can say that this information it is called mutual information is justified, because information is mutual. I mean, either way you look at it, really you get the same expression, same value. I take one more specific example of a discrete memoryless channel, and I am calling it as binary symmetric channel, BSC. It's a very popular channel model for the beginners. Okay, binary symmetric channel. I have drawn the diagram in a somewhat different manner, but it should not be difficult for you to understand. Okay, as if, though it was not necessary, but as if this portion is my TX side, transmitter side, this portion is my receive side, okay, and this diagram indicates the channel behavior in some more detail compared to the earlier diagram. Which way? I have indicated the events x at this side, y at this side. You may also prefer calling it, because I have drawn arrows, you may call this as the input side to the channel, this is output side of the channel, okay. And then, so x is the input event from the input experiment, y is the output event, and the input has got two possibilities, okay. The input will be either x1 or x2. So essentially we are talking about a binary situation, okay. This may be 0 or 1, x1 may be 0, x2 may be 1, or vice versa. So there are two possibilities at the input, and the channel is such, it is a nicely behaved channel, I should say, that it also gives either of the two possible outputs. It gives either y1 or y2, okay. And if you now think about in a common sense manner, if I transmit, if I send say a 1, binary 1 through the channel, and the channel behavior is very nice, then what should I get at the channel output should also be something as, which can be interpreted as logical 1, isn't it? It is hardly the situation that when I transmit 1, I receive 0 at the other end, is it not? Okay, that situation, that because of the behavior of the channel, because if I remember, the channel introduces some kind of undesired form of uncertainty. I made this comment earlier, isn't it? So if you remember that, then something wrong may go place in the channel really, and because of which, even if I had transmitted a logical 1 at this point at the input, I would have received a logical 0 at the channel output end. So there is a probability, okay, there is a probability which is known as the transition probability. I am indicating this by epsilon here, small epsilon. This epsilon gives me the probability that when x1 is transmitted, you receive y2, okay, and epsilon we will see that for good reason it should be small, much smaller really, but usually when x1 is transmitted, we are supposed to receive y1. Similarly, when x2 is transmitted, usually we will receive y2, but occasionally we may receive y1 as well, okay, and that is a case of error. The channel, I say the discrete channel causes error, okay. So when the channel does not cause any error, x1 results in y1, x2 results in y2, fine. Now this channel is called as a binary channel because the input and outputs alphabets are of size 2 each, okay. The channel is also called symmetric. Can you guess why? Is the same, okay. The probability of error, okay, from 1 to 0 and 0 to 1 is the same. Does it happen in the physical situation that the channel is not partial to whether 1 is being transmitted or 0 is being transmitted?
Yes, sir.
Does it happen?
0 is easily conveyed, but 1 is.
So it does not happen. It is
How?
biased. It is
You are agreeing, you are saying that it does not happen. I mean the channel is impartial to 1s and 0s.
no, it is not impartial.
Not it's partial. He is also saying that the channel is partial. 0s are easily transmitted than 1s.
The most likely, if you are going in a TTL logic,
Yeah.
then 0 is mostly conveyed, but 1 is sometimes not.
Why? What is the reason?
It might depend on the coding scheme.
I am not talking about 1 bit at a time, and we have already said that our channel is memoryless. It does not remember what has already gone through. It's a discrete memoryless channel. A specific case of that we are now considering, a simple case. So there is no, I mean, I need not worry about what has gone earlier really. So no question of coding, etc. We can talk about one symbol, 0, 1 or x1, x2. Anybody supporting their views? You support? You feel that okay, zeros are transmitted more easily than 1?
At least we are
biased.
giving it a TTL logic. The example is a TTL.
Well, no, there is no reason as such that the channel will be partial to zeros and ones. There is no reason. It's only fundamentally when it comes to communication, more interest. I mean, good quality communication systems really. the channel usually does not have, there are exceptions, I will tell you, usually does not, is impartial to the symbols which are transmitted. In fact, that is the job of the communication system designer to ensure that the waveforms, the logic 1s and logic 0s, they are given such shapes that the channel behaves impartially. Let me put it that way.
But this is not actually which is happening.
Actually, it happens like that. Actually, the channel is impartial. The channel is impartial really, because my question is, if I know that the channel is going to be partial to zeros and ones, I must try to give different voltage levels or different form to ones and zeros, so that the channel does not show up this partiality. Is one common way of thinking really. Okay, if I want to view the channel as memoryless. Yes.
Like in a TTL logic, if
Yeah.
the table is very long, then there is sometimes differentiated, because when there is a zero transmitted, there is.
That's a good point you have added, that when the cable is very long, okay, when the cable is very long, its effective bandwidth reduces really. Okay, because the cable can be modeled as, you have studied network theory a little bit, transmission lines. The cable can be modeled as a distributed parameter line, okay, and can be viewed as kind of low pass filter for baseband transmission, and the cutoff frequency comes down, it becomes lower and lower. So for the same pulse at the same bit rate, now the pulse shape becomes more and more rounded, which means the pulse energy goes into the subsequent bits, etc. And I say the channel is now exhibiting memory. We are not talking about that kind of channel. We are talking about the channel, okay, that's our starting assumption, that the channel is memoryless. So, okay, so in such memoryless channel, usually there is no reason why the waveform should be treated partially. Okay, in fact, there should be scope. If I know that the channel is going to be partial, I should take care of that really. Okay, so coming back to this point really, there are situations, as he says, a very long drawn cable. Perhaps you have gone to a distance which was not recommended by the service provider, or even in some cases of optical fiber communications. In optical fiber communications, in some cases the channel becomes a bit partial. Even for conventional systems, if your design of the demodulator, where you are using some large value capacitance, etc., if you think quickly about an envelope detector in AM, you may get some kind of close resemblance, where you are using a large capacitor which may get discharged, may get charged because of some long runs, as he was saying, of ones over there. That brings in some kind of memory, local memory over there. But we are not talking about those issues there. When the channel is memoryless, usually, I mean, ones and zeros are treated equally, and hence I am saying this channel is, I am calling as a symmetric channel. Okay, binary symmetric channel. The probability of, pardon?
Shouldn't it be this Px1 x1 by 2 epsilon by 2 equals Px1 x2 by 1?
Here is it? Here x1 y2, yeah, yeah, it's y1 x2. That's the change, isn't it? Right. So for this binary symmetric channel, now the value of epsilon is usually very small. Now we can see that these input probabilities of ones and zeros, they are equally likely, so they are half. So I can now calculate the joint probability when these probabilities are known. Note that these probabilities are these conditional probabilities. Probability of y given x, probability of y1 given x1 is 1 minus epsilon, probability of y1 given x2 is epsilon, like that you should interpret. This is the symbol. We are talking about this kind of conditional probability. So I can come out with the joint probability after deciding about the individual probabilities, and we are assuming that they are equally likely, x1 and x2s. I can now find the probability of y1, okay, probability of y1 after finding the conditional probability which is given, and the probability of x1, and I can find that probability of occurrence of y1 and y2 as the same. P of y1 is equal to P of y2 is a half. So to summarize, binary symmetric channel is a channel wherein the inputs, if they are equally likely, the outputs are also equally likely. Okay, fine. So the property of the channel is not reflected in the final output probability, okay, but is reflected if I consider the information associated in such cases. I am continuing with the same example. I am also calculating the other kind of conditional probabilities for you, and then ultimately I am finding the mutual information between x1 and y1, that is the probability and the information associated about the occurrence of x equal to x1 when I have received y1. Please interpret this. Ixy x1 semicolon y1 is the information about x1 I get when I have actually received y1 at the output. Is that okay? That should be the interpretation of this mutual information. Okay. We can see that this information expression comes out to be log 2 to 1 minus epsilon. You should devote some time in sort of elaborate interpretation of these expressions. So, Ixy x1 semicolon y1 is the information about x1 we get after we have observed y equal to yn at the channel output. And just now we saw that it is the same information I would have got about the event x equal to x2 after observing that I have got y2 at the channel output. So, this is one kind of information, mutual information I could ask for from this binary symmetric channel. The other kind of information I could expect is this Ixy x1 semicolon y2 is the information about x equal to x1 at the input that may have occurred when I have actually received y2. That means I have received y2 and I am trying to find out, guess what was the probability that x2 or x1 was generated by the source, okay, or equivalently that I have received y1 and I am trying to find what was the probability that x2 was generated at the source and was launched in the channel. So, these are the two different kind of information one may be interested for this binary symmetric channel. Is that okay? Fine. Now, a little bit of interpretation on these two expressions before we stop. Though I wrote earlier that epsilon should be a very small quantity, okay, but if you consider certain extremities like epsilon equal to 0 to start with, you can quickly tell me what is the situation for the binary symmetric channel. Can you give a name to this binary symmetric channel? Ideal channel. Epsilon is 0. That means if x1 is transmitted, y1 must be received. x2 is transmitted, y2 must be received. There is no question of any error. Okay, so it's an ideal noiseless channel. Okay, do you get it? Do you get it ever? So epsilon equal to 0 is a theoretical possibility. Okay, in practice, epsilon should not be 0 really. Okay, we'll stop here. We have a few more observations to continue really before we go to the self information and certain other properties. Thank you very much.